a plant, a light bulb, another light bulb, the sun. All these are objects that have light, whether it is the light source itself or it is just an object that we can see because the light is reflecting on it. But what light actually is it a particle that has mass, or is it wave, pure energy? Can light become pure? And if it is, what can we use light for if we know more about how it works?
This is visible light. Visible light waves are the only electromagnetic wave we can see. When all the waves are seen together, they make white light and shines through a prism. The white light is broken down into colors, as we can see in the picture, which are violet, indigo, blue, green, yellow, orange, and red. Now let's start with properties of wave. Properties of wave include wavelength, frequency, and amplitude. Amplitude is the vertical distance from the midline of wave to the peak or trough. Wavelength. Wavelength is the distance between identical points on successive waves. And frequency is the number of waves that pass through a particular point in 1 second. Now let's talk about electromagnetic radiation. Electromagnetic radiation is the emission and transmission of energy in the form of electromagnetic waves. As we can see in the picture, there are many kinds of radiation, such as gamma or X-ray, but we can only see visible light.
Speed of light in vacuum. C is a constant which is equal to 3 times 10 to the power 8. The unit is meter per second and C is equal to lambda times nu. The speed of light is the product of the wavelength and the frequency, which wavelength and frequency are inversely proportional. Planck's constant h is equal to 6.63 times 10 to the power negative 34 joules second. E, which is the energy, is equal to h times nu or h times f. H is the quantum of electromagnetic action that relates a photon's energy to its frequency. Energy and frequency are directly proportional. Planck analyzed data on radiation emitted by solids that are heated in various temperatures. He discovered that atoms and molecules emit energy only in certain quantities called quanta. Quantized energy. When solids are heated, they emit radiation. Wavelength and distribution of the radiation depends on the temperature. Max Planck assumed that energy can be released or absorbed by atoms only in chunks of some minimum size. The smallest quantity of energy that can be absorbed or emitted as electromagnetic radiation is called quantum.
Now, Planck quantum theory is going to be some planks that help making a bridge for Albert Einstein's discovery of photoelectric effect. There was a debate arguing about whether light is particle or wave, and Einstein got to cover with that and he found out that it is both, baby. He discovered that light is energy packet. We call it photon. Light sometimes behaves as a particle and wave as well. He discovered this with photoelectric effect experiment. What he did is that this is Albert Einstein, baby. So I set up the positive charge terminal facing with a metal surface. I then charge the radiant energy, transferring energy to an electron of the metal. Now, the electron of the metal have excess energy. Therefore, with the sufficient energy, the metal emits those negative charge energy. I know that the energy comes out because the positive terminal receives those energy, and I can observe those energy with the current indicator. The diagram shows that HV is the radiant energy shines onto the metal surface. Ke is the kinetic energy of the ejected electron. W is how strong electrons are held in the metal. E is the energy of photon. The equation E equal to Ke plus W is basically HV equal Ke plus W. With this formula, we can apply the calculation to answer many questions, and that light is related with electromagnetic wave.
Bohr's model explains the spectral lines of hydrogen atomic emission spectrum. There are two types of spectra, continuous and light spectrum. The continuous spectrum contains energy of all the wavelengths, while light spectrum only contains wavelengths corresponding to certain energy values. The light spectrum is also divided into two types, which are emission and absorption spectrum. The main difference among these two light spectra is that emission spectrum is electromagnetic radiation emitted due to the transition of an atom from high energy level to low energy level, and the absorption spectrum is the transition from low energy level to higher energy level. Both models of the atom can help you understand the difference too. If the electron moves from low to high energy level, then it has to absorb energy to be excited. Inversely, when it moves down, when the electron moves down the energy level, it will release energy out so that it could move to the ground state. Or state that the electron only circle around the nucleus at a specific orbit designed by quantum number n, or energy level. This quantum number n can be an integer in which n equal to 1 is the orbit closest to the nucleus. Bohr also came up with the relationship between quantum number and the energy of an electron. En equal to negative Rh multiplied by 1 over n power 2, which Rh is Lindbergh constant. We can combine the formulas that associated with the change in energy to find the variable that we want to know, because energy change and frequency associated with changing values of the quantum number n.
Application: X-ray. X-ray is a type of radiation called electromagnetic waves. It shows a picture inside of our body in different shades of black and white because different tissues absorb different amounts of radiation. Production: in a tube, a heated cathode, electrons are emitted and moved to strike the metal anode. As a result, X-rays scatter from the anode. The tube is evacuated, allowing electrons to move without colliding with air molecules. Typical produced X-ray wavelengths are 10 to the negative 3 to 1 nanometer. X-rays are produced in two ways. Number one, when electrons are suddenly decelerated, they produce X-ray. The produced rays are called Bremsstrahlung radiation. Number two, when electron makes transition in heavy elements, generally between lower atomic energy level, they produce X-ray. They are called characteristic X-ray.
The characteristic X-ray process depends on the target material, while the Bremsstrahlung process depends on the accelerating voltage. Every spectrum that stems from an element is characteristic of an element, since each has unique atomic energy levels. The elements that produce characteristic X-ray spectra are heavy elements and within their inner shells, which the related energy levels are about 100 to 1000 eV. The spectrum of an X-ray contains the Bremsstrahlung part and the characteristic part.
I'm going to show you some problems that are related to X-ray. The question is, in the process of producing X-ray, the kinetic energy of an electron projectile, which is equal to its total energy, is transformed to produce a Bremsstrahlung X-ray photon on impact with the atom. If the entire energy is used, then an X-ray of maximum energy, maximum frequency, and minimum wavelength is produced. So, if we know that the bombarding electron is accelerated under 10 kV, then what is the speed of the electron along with the wavelength of the X-ray? First, we have to know the formula. E is equal to electron voltage, EV, in which E is the charge of the electron, which is equal to 1.6 times 10 to the power of negative 19 coulombs. And V is an electrical potential difference, or the voltage. Second, the question also mentioned that K is equal to E, so we can come up with another relationship, which Ke is 1 over 2 mv squared and E is h nu. After we know the formulas and the constant, we can substitute the values that we know and then find the speed of the electron. Next, after we know the speed of the electron, we can calculate the X-ray wavelength. Let's use E equal to hc over lambda. We want to know the wavelength, so we can set our equation into lambda equal to hc over E, which h is Planck constant and c is also the constant for the speed of light in vacuum. After we know the formulas and values, we can plug in the number and calculate for the wavelength of the X-ray.